So, good morning and thank you for the introduction and also accepting my late submission. It's a pleasure to come here and give you this talk. I will start. Let me also acknowledge my co-authors. I've used quite a lot of material that I'm talking about, especially from Gani, and also these are two collaborators who used to work for me. Now he's in Hong Kong and he is working in Novo Nordisk in Denmark. So I will start with a big picture, and what I'm going to talk about is actually in a paper that will come out very soon. And if you like what I'm saying, you can read this paper, you will find all the information. And I like to start with a good, positive picture. And what I say is that we human beings are the master of this earth. And the question is, how did we get there? Chemical engineering has a positive contribution to this because we provide all the products that the society needs for their sustainability. So here we make a big contribution, and one can see that these are products that have to be made, and so we also need to know the process that will make it. And so we come to this product tree where one can see that we start with some basic material, and for example biomass, one of the topics of this forum, and from biomass we want to produce different products. As we go up in the tree, the value of the product increases, the amount of product needed decreases, and so one has to see which is the best way to get the product and how to obtain it. So one of the questions that one can ask is what, why, when, and how. And also one can see is that if we go higher, these products have higher price than these products. So if we want higher value products, we always need to go up, and we need to look for the raw materials below so that we can make a profit. And then you can see here the product price increases as we go up. The molecular size also increases as we go up. Number of alternatives also goes up. On the other hand, the production rate goes down. We need to make less for higher value products. So these would be then batch processes, these would be continuous processes. An interesting topic would be from biomass, how could we get something here, for example methanol, and then using methanol, how can we get almost all the products we want? Could this be possible? And how much methanol do we need in addition to the methanol that we are producing now? So let me also show you a classification of products that we have made. The first type we call single species. It's single molecular type. It can be small molecules, it can be large molecules. Then multiple species, that's a blend or mixture. And then devices where chemicals are used for the operation of the device. I will not go through all the items of this, but related to the process, important factor is the cost of production. And that means the process. Can we have a process to make these small molecules or large molecules in a cost-effective way that will also be efficient? And if you think of this, these are basically almost all the bulk chemicals, ethanol, methanol, all kinds of chemicals. We need to have the process, and we need to know the raw materials to make it. But if we look at the formulated products, these are also cost related, but also the product functions are important there. So if we are talking about detergent, it has its function. At the same time, it needs to be produced. Then we have the devices. They are mainly functions. The process is not that important. The important is whether they can perform the functions that are needed. And the last thing that I want to highlight here is the risk, especially if we are talking about these kind of products. Do we have enough feedstock availability, and what kind of impact it is going to make to the environment or sustainability? In the case of formulated functional devices, unfortunately, we can say that at the moment, the engineering science knowledge is not enough to make computer-aided things. It's more correlations, experiment-based work. So with that, let's see the problem definition. What is the connection between the product and the process? What we see is that if we want to convert raw materials to products, we need a flow sheet, operating conditions, equipment parameters. But this product has to match the product that we have designed in terms of its properties and functions. And this product comes from atoms, molecules, and mixtures of atoms. So there is a definite connection between the product that we are going to make and the product that we have designed. One item that is not discussed quite a lot, but indirectly it's actually used, is does the product function in the way it was designed for? So if we are talking about a solvent, does it actually separate? If we are talking about a drug, does it perform the biological activity? Or detergent, all this. And that is the performance function that we need to check. So which means that if we apply the product through a process, does the performance match with the functions? And this also needs to be checked, and this is also a chemical process that needs to be modeled and analyzed. So what we have developed together with Kai is what we call a grant model. Here is the process-related models, equations, everything that you can think of. Here is the product-related things, quality and manufacturing cost related, other factors like company strategy, societal needs, economics. All of this together gives us the grant model. If we can put all these models together, then we can solve this as covering almost everything related to the product design development. One thing that we were not still sure how to include the sustainability. Now we have added the sustainability, not as part of objective function, but as a set of constraints. So does the product also satisfy the criteria of sustainability and environmental impact? And in the papers that I've mentioned, we have an example, so I won't go into the details of this, but we did solve one problem where we have taken all these aspects of the model. But it's a simplified problem, so it's not thousands of equations. Okay, so I will also show you the problem formulation in a slightly different way. I'm not showing the equations here, but just what kind of equations there are. We have an objective function, we have the process constraints, then we have the process model, that is the mass energy balance, property models that we need to satisfy the properties, process variable constraints, molecular structural constraints, as well as the flow sheet related constraints. So all of these are part of the grand model that we talked about. And then we can see that different equations here will do the product design. That means equation 4 and 6 together with the objective function, we can make the optimal product design. These equations together with equation 1 will give us the optimal process, and all of it together will give us the integrated product process. And I will show you examples of subsets of these equations forming different types of problems that we would like to solve. So the concepts, in a very simple way, how does the molecular design work? That is the product design. Let's say that we want to replace benzene, which is a good solvent, but is not good for environmental and health reasons, and we want to replace it with something that works better than benzene, but is not harmful. So this could be compounds with carbon, hydrogen, oxygen, and non-aromatic, non-naphthenic. So we say we want acyclic alcohols, ketones, aldehydes, ethers. These compounds can be made from these functional groups. If we combine them and join them together, we can make molecules. One example is this, but this molecule can be represented in different ways. And once we have this information, if the same groups also predict the properties, we can immediately see how many of the molecules we generated satisfy our requirements. Then we have designed the molecules according to our properties, given properties, and then we can check whether it works for the process that we have designed for. So if we look at it from this general problem formulation, this we can see now from the CMD problem how many different ways we can solve it, and I will show you all of them. So we can simply go and say, let's, instead of generating the molecules, let's go to a database which contains a lot of molecules and properties and check which molecules satisfy. So that would give us one form of results. Another form, like I showed you, we can do generate and test. We generate the molecules, we test them. Or we can send it to an optimizer with all the mathematical equations and let the optimizer solve it. So we have all three options that we can do, including hybrid, where we combine different options, meaning that we can get better estimates with the database search and generate and test and then solve the optimization problem. So with that as a background, I will highlight all these things with different examples. And on some slides I will go through fast because of the time, but if you are interested, you can get this copy and see the equations and also the papers where all the equations are given. So the first one I will talk about is highlighting the molecular design, that is equation 4.6 with equation 1. And we want to design a surfactant. And a surfactant is used, for example, in a detergent or many other products, cosmetic products. So what kind of problem do we want to solve? First, we need to say why we want a surfactant and what are its needs. We have to transfer these needs into a set of properties, and then we have to choose the building blocks that will make us the surfactant. In this case, what we are saying is that we will start with what we call a backbone, and then on the backbone we will add the other items of the molecular structure. And then the properties that we want it to satisfy, their upper and lower bounds are given. So now we want to generate molecules and we want to see which of these satisfies. As I said, we have the molecular structural constraints. These kind of constraints tell us when we join the molecules, it will be a stable chemical molecule. And these are the properties, these are the structural constraints, these are the property models, and we have some extra constraints that I'm not showing. These are related to, because we are generating complex molecular structures, we need these kind of constraints as well. The total size of the problem is more than 1 million, but what you can see is that we have made the property constraints in such a way that these are linear constraints. So it is not a problem to solve it. Even though the model is nonlinear, it can be, without any simplification of the model, we can reformulate it as a linear equation. And we have solved it. And this is the molecular structure, this was the backbone, and then all the properties that were obtained. In a similar way, what we can say is that this is the benzene ring, and we can make what is called a benzene dog, which you will find in almost all pharmaceutical and pesticide kind of products. Because the benzene ring is toxic, and in these kind of products you want to kill some bacteria or virus, so you need it to be toxic. So the next problem, I will not show you, this is product recovery, where it is mainly the process-related issues that we have done a reaction, and then from the reacting medium, we want to extract the product. But you can see it afterwards in our papers. What I will show you is the example of solvents for separation. This also has to do with energy. So now we are using both the process part as well as the product part, because we will want to generate a solvent as well. So first, let me show you why we are doing this separation. And here we have an expert on distillation. I hope he will agree with me that as we increase the purity of the product that we want, what we have seen is that the amount of energy required increases quite a lot. So which means that if we operate up to 95%, the energy required is not very high. But if we want to go to 99%, that final bit of purity requires a lot of energy. So what we have tried to see is that can we use distillation up to here and then change to something else over there. And that would be a hybrid process, giving us more energy efficient. And then the question is, what kind of, if we use membrane, what kind of membrane should we design? And then the product design problem is that we want to design a membrane, but our process actually is a different process. So we are not talking about manufacturing the membrane, but making this original process more efficient. And then different hybrid scripts can be formulated, and in each case we need a mass separating agent that we need to design, which is a product design together with process design that helps us to get a more energy efficient separation. So this example is with membranes, but if we want to do a separation, similar kind of separation, but not with membranes, with solvents, we could say that we have a solvent which gives us a distillation boundary here, and a product, solvent rate that is defined by this line here. The point of intersection gives us the amount of solvent. Then one could ask, is this a good solvent? And the amount of solvent required is quite high. If the solvent required is high, it will require more energy in the second column. And also the heat of vaporization of the solvent will influence how much energy is needed here. So could we reduce the amount of solvent and find a better solvent? So what we can do is we can pre-design, assuming that, let us say that the distillation boundary would be this. Then the solvent required would be here, and we can pre-calculate almost everything. And then the question would be, can we find a solvent that will give us this phase diagram? If it does, we already have a very highly energy efficient system. And this can work not only for organic solvents, but also ionic liquids. We could say, can we find an ionic liquid that will do this? Then this part of the column would be almost zero energy. So what we are doing is combining the product design into process design and making the process design more efficient. And in the case of this separation, which was acetone chloroform, we can also find not one solvent, several solvents, and then set up an optimization problem to find the best solvent, either pure or mixture. The optimization then will give us, together with all the energy required. And this is one of the solutions. So the next one is specific operations. That means, and here also we can see that we are designing the solvent or the membrane, but the process is actually applying it. So we are not talking about the manufacturing of the solvent, we are talking about applying the solvent. So it's a different kind of we are checking the performance here. And here also we will do something similar, and this is a very common problem, that we want to change or find a substitute for a refrigerant. The Freon or R134A needs to be replaced. Can we find a better one? So we know the refrigeration cycle, we know the thermodynamic phase diagram and how it works. We use these and we take the properties of R134A and find out which properties we would like to keep and which properties we would like to change. So then we identify all the properties we want with their lower bounds and upper bounds. So, which means that any refrigerant we find must satisfy this. In addition to this, we also put the process constraints now, that the process here has to work at the highest efficiency. So we include the process model and also the objective function for the process. So this has to be as high as possible. So now, together with all of this, we solve the entire problem. So we get the refrigerant, we also get the design of the refrigeration cycle at which we will get the maximum efficiency. And also all the environmental constraints will be satisfied. So we can solve it in different ways. We can linearize some of the property models and solve it as a MILP. We can solve the design of the refrigerant and get a number of candidates, and then for each candidate we can solve the process design. Or we can solve everything together. So what we did here was we solved this first, then this, and then used this result as initial estimate for this one, because that's a complex MI and LP problem and needs good initial estimates. And so we can reduce the search space as we go from one problem to another. And then here are the results. This is what we know already. This, by the way, the program generated all of them. So even though we know this, but the program generated this molecule. So then we found another one, which is also known as a refrigerant, but you can see that the global warming potential is not good, and the atmospheric lifetime is also not good. But on the other hand, the efficiency is quite high. Another one we found, the efficiency was lower, the global warming potential was not good, but these two are quite good. They are known as, they exist as chemical compounds, one can buy them, but they are not known as refrigerants. So it would be worth testing on a real cycle and see if it works or not. So then comes the question of tailor-made. I talked about pure single species products. Now comes mixtures, and we have worked quite a lot on liquid formulated products like cosmetic products, detergents, things like that. But I will highlight the tailor-made blends related to fields, and also emulsified products, but I will not go through that. And here, these are the equations that are used. So this kind of products means that we have a base product. Into the base product, we will add some chemicals, maybe from renewable sources, and we will improve the quality of the product, final product. So if it is gasoline, we can check with the car manufacturers what would be the ideal gasoline properties, and then we will try to see if we take a main gasoline blend and then add some other compounds to it, can we improve the quality? And so the more we can add the renewable compounds, the better it will be, because the less would be the fossil fuel additives. So that can be done for gasoline, diesel, jet fuel, lubricants. I will show you the example of gasoline very fast. So the properties that would be needed are these. These we can find from the car manufacturers as well as the books. And then we need models for each of those properties. So we have developed the models, and then we have a base oil, we add additives, and then we make the tailor-made. So why 22? Because we can actually add thousands of molecules. The reason we add 22 is that these are renewable chemicals. That means it can be made from renewable resources, and processes are known or reactions are known, so they can be made. So then we have the miscibility constraints, optimization with respect to the properties. I will not go into detail, but what we do is we have a decomposition approach that we take the pure compound constraints and see which compounds satisfy. Then the miscibility constraints, that means that whenever we mix all these compounds, they have to be one phase. So that is very, very important. Then the linear constraints, and finally the nonlinear constraints. And as we go along, the number of alternatives reduces. So when we come here, it's a small, well-defined problem that we can solve through optimization. And the results are given. Some of them have been also experimentally verified. So we are here collaborating with Qatar University, Texas A&M University in Qatar. They have all the facilities to measure the properties, so we have confirmed them also by experimental verification for gasoline, for diesel, for jet fuel. Hopefully I will not travel on that jet using the jet fuel. Okay, some interesting other developments, the chemical product simulator. So all these things I'm talking about, we can think of just like a process simulator. Can we think of a product simulator that you can put your product information and you can calculate all the functions, the properties, even design the product and things like that. So we have made the first prototype of that. We call Pro CAPD. It can do product design, analysis, search, performance, all these options it can do. And this is how the prototype screen looks like. Just like a process simulator, it has all the options for product simulator. And I think it can be quite interesting. And you can, if you are interested, you can also try it out. We would be happy to give trial versions for you. So some other things related. One is I started talking about the biomass and to get the different products that one would want. We can represent it as a network of processing paths. Here are the biomass, here are the products, and it has to go through a number of steps. Each step involves different operations. And we have a network like this in the same way that I showed you before. If we have models for each of these boxes, we can set up a big optimization problem and then see for which biomass, which product would be the best one to take. And then what I want to emphasize also is that although we do work with computer-aided and think that our models are the best and can do everything, it still needs experimental verification. And we still need to incorporate experimental verification into our approach. And what we have done is we say that for every problem, we will use the computer-aided approach to get very fast to a solution. And then we will use the experimental resources on focused experiments to verify and improve our results. In this way, we are not neglecting the experiments, but they have a purpose, and we are not doing the product design or process design with blind experiments. We are doing with focused experiments. And in most of our algorithms now, for product design, we have the element of experimental verification. Some problems that we still cannot solve. Functional products, I will show you also another problem here. The properties for different functions are sometimes almost impossible to model because we do not know enough theory on it and there is not enough data. Formulated products is the same thing. Applications in life science related products, not enough theory is known to develop computer-aided techniques. And devices is the same thing. And I just give you one example with respect to emulsions. If we could make a figure like this, it's called a fish diagram, then we could actually design products quite easily because margarines, which is oil in fat, should be here. Microemulsions, cosmetics and things like this should be here. Drugs and detergents, things like this should be oil in water, should be here. And if we want a good reaction system, we could have a homogeneous reaction system over here. But getting this kind of fish diagram, at this moment, there's not enough data to make it for any new system because it involves oil, it involves water, it involves solvents, product chemicals, as well as surfactant. If we ask experts in thermodynamics, they will say maybe another 20 years before. But how can we get this data and model in so that we can do the product design very fast? Is a challenge that we have to face. I think I will skip this, but if you are interested in the timelines, it's a very biased timeline, I would say, starting from 1965 in process synthesis all the way to 2015. We put this in our paper. We indicate some of the important developments, in our opinion, related to product process. So you're welcome to see that in the paper. And this is for product, this is for integrated process product. So finally, with all of this, I will come to this example. This is Dove Beauty Bar. It's a soap. This comes from the early 1955. And it is there, it is being produced, but we still do not have computer-aided techniques to optimize this process. It's still by experiments. And what does the soap contain? The functions. These are the functions the soap needs. And for the soap bar processing line, these things need to be satisfied. For the soap bar contents, these need. But up to now, this is still optimized by experiments and expertise within the company. And this is just the soap bar. Think of all the other products like that. So we need a lot more work in modeling to get these things optimized. So then something about the future, since it's also related to this topic of the forum. Our population is going to be around this, meaning that we need big increase in the GDP, requiring bigger production capacity, more energy, more water, more CO2. So despite all of this, we have to advance, but we need to address these things. And something to think about, I think the one who made this cartoon did not know the modeling work that we do, because every time we have a problem like this, all we need to do is put a parameter, measure some data, and fit the parameter. So we perform the miracle almost few times every day. We do have a lot of data, but probably we are not using the data properly. And we need to use the data more efficiently. As well as those who measure the data, they should measure it with a plan. Without a plan, the data is useless. Then there are uncertainties in the model and data, and this can happen. You know, there is a bridge between Sweden and Denmark. When these two sides were building and they needed to be combined, we were worried about this. Until the last moment, they were worried about it. So it's a real problem. And finally, I would say that as technicians, scientists, technical problem we can always solve, and we can find a solution. Like this scientist has changed one molecule in a painkiller and got an excellent hairspray. But the question is that we don't decide about the product, somebody else decides the product. I think we should decide, we should take responsibility. So with this, I end my lecture. Thank you very much.
Thank you, Rafiq. The floor is open to questions. Yeah.
Good morning. Thank you for the very interesting presentation. I would like to ask you, what kind of suggestions can you make for the process design?
In what way? What kind of problem
For
are you talking
example,
about?
can you make a suggestion only about the downstream processing? Something about the reactor? Can you propose a catalyst design?
At this moment, the way we are solving is that we need to start with the reaction information. So we would not design the catalyst, but we can say if a catalyst was found and could give a conversion of, let's say, 90%, the optimal design of the process would be this. So the catalyst design is responsibility of somebody else.
And what about, does the catalyst have an impact on the product structure?
Definitely, yes. So that's why most of the process design would already fix that we have found this catalyst which would say to operate at this temperature pressure, and this would give this product with these byproducts. Then, so choice of the catalyst will fix all of this. And then one could say that if we find in the literature, especially converting biomass to useful molecules, we may find 10 different catalysts, including catalysts. Then we could optimize and see which is the best catalyst. But we are not, at least my group is not designing the catalyst.
Very comprehensive and impressive presentation. I have one question concerning the topic that you also addressed, including experiments. Specifically when it comes to the group contribution methods, providing an estimate of the, let's say, liquid immiscibility at that point. How good are these estimates?
That depends on the chemical systems. So especially for liquid-liquid systems, one has to check how good the model is. It's difficult to say. I would say that most organic chemicals, probably it works well. We have been looking at lipids now, and then the parameters are not good, so we have to re-estimate the parameters because the groups are the same.
Thank you very much for the talk. I was wondering if you can include constraints on the molecular design with respect to something like chemical stability of your product. Do you include that in the design?
Yes, because the octet rule, all these things that we have put, we claim that we can guarantee that this would be a stable chemical, and somebody should be able to make it, synthesize it. But we don't provide the synthesis route.
Yeah.
Your graphs often remind the onion diagrams. Do you imply any link between your approach and this other?
I would say that the onion diagram, in a way, it is, I don't think it is, we are using it in the same way as Douglas, but the principles is the same, that we have a search space and we are trying to reduce the search space by finding which are the constraints that will help us to go this way. So it's a hierarchical approach in terms of setting up the constraints. So as a very simple example, with the molecular design, we can say we have 20 groups. And then the structural constraints will define for us how many molecules we have. So that defines the space. Then we put the properties that we can directly calculate from the molecular structure. And those that will satisfy will reduce the space. Then we will calculate some other properties that are functions of the molecular structural properties that will reduce the space further. So this is the principle we have used. Which constraint set will reduce? We don't need to go up anymore, we just go down. And then when we come to the final core, we have the best candidates. We can do experimental verification, we can do optimization, we can calculate the objective function for all of them and order them to find the best.
So a quick question. The example you just said, and you gave an example of a surfactant, phenol and a penguin group.
Yeah.
So there you did specify the total number of the chain length, because you have 20 different things. They could be much, much longer than what
Yes. When we do this, we say, because if we say the number of groups can be minimum 2, maximum 100, there would be billions of alternatives. But indirectly, we say if that the molecular weight should be less than 400, or the boiling point, because the molecular weight boiling point is directly related to the number of groups. So like that, we reduce the size. Yes.
When you need molecular design with the process design, for the part that you need to purify your product, how do you decide if you need extraction or distillation in water?
Yeah, that's a good question. We have not resolved it. We fix the process design that we do at this moment is for a fixed flow sheet. So it would be interesting to say, and that's why I showed the refinery network, because if we put the product together with the network there, then it will choose also the processing route. At this moment, we fix the processing route.
Okay, so I think that we have to move to the next presentation. So thank you very much.